Well,
I made only mac and cheese in the oven.
it's baking right now.
No, I've like baked it this weekend, so it's not oven too. They told me
So,
to put roots on top, like crushed up.
Was your weekend relaxing, or this question is too sarcastic? When I was.
Did you get anything this weekend?
Well, I hope all hard things are already behind, and no. Well, in this class.
Oh, no.
No. Well, presentations are not hard. What is hard is to answer questions if there will be like unexpected visitors.
You should not invite
Advice.
visitors. Don't invite visitors.
You could tell the wrong time.
Yeah, say that we're presenting. You should say that we're presenting at like 3.
Yeah, sure.
She doesn't have any connection to you though, so she won't know.
Sure. So there are, I have plans which would fit another semester, but we have only 2 meetings, and I will try to squeeze as much as possible. So there are 2 things to make you accomplished physical chemists and quantum theorists. These 2 things are spin and spin operators for in the same way as we did for harmonic oscillator, weather spin operators. And on Wednesday, there will be Frank Condon principle, which is needed for those of you who are looking for UV visible spectrum. Both of these subjects are tightly related to like half of the projects. So if we would have these 2 meetings before you write reports, maybe it would benefit them. But I do not have control on the length of astronomical year. So if I should probably speak more and show less, but the actual material and slides which have been sent to you by email, which I will show here, they're very, very boring and math related. So they are useless without appropriate discussion and comments. So focus, let's better discuss things, and then I will skim through and point right things, but math without discussion is not useful. So there are, I'll just show what would be expected outcome of the meeting if we have enough time. But again, it looks boring, and you probably do not enjoy it. It's like digital set of zeros and ones and some angles. What is the goal? Like what were we going to, and what is our fundamentals, on which cornerstones we are staying together? So the goal is the not from this class, but from your kindergarten everyday general education. What are the 4 quantum numbers for hydrogen atom, hydrogen molecule?
Magnetic, spin, momentum, and
Principle.
Right?
So it's kind of opposite direction. Typically, one starts with principle, and we kind of covered principle in our discussion of Bohr's model, not quite, but in some extent. And for orbital and magnetic, we did this rigid rotator. So we are not yet fully covered it, but we covered 3 partially, and we didn't cover spin. So if we want to be practicing chemists, we need forced quantum number spin. Right? So there are some effects where you cannot neglect spin. What are those effects? Gauge is expected to want.
That's the problem.
Huh?
Zeeman effect.
What's the problem?
Zeeman effect?
Yeah. Oh.
I remember your paper.
Welcome. Good, good. Zeeman effect is like fundamentals, but if you are involved in everyday wet lab research practice, which characterization technique cannot be done without spin?
I don't know.
Yes. So the purpose of today's meeting is to be somewhat literate in the NMR. One reduced length meeting is not enough to be like masters of an NMR, but some general ideas. So this is a goal. What are the cornerstones? We cannot. It's too late to start from the beginning. We should like build up on what we have. So one cornerstone is rigid rotor, angular momentum. We'll logically try to establish connection between rotation of rigid rotor and spin. And second cornerstone is technique of ladder operators for harmonic oscillator. Remember, if you apply ladder operator to lowest state, if it is lowering operator, it gives you 0. If it is raising operator, it promotes you to higher excited state, right? If you take excited state and apply lowering operator, it drives you down. And then all useful operators like position, momentum, energy can be expressed in terms of ladder operators. It's a little painful, but possible. So like 2 operators control everything for harmonic oscillator. There is a very much of similarity for spin. So if you are doing records, you may record it. So 3 things. Goal is NMR. Cornerstones are rigid rotor and ladder operators for oscillator. Likely we will not go. We will not have time to go to this last slide. So it is a personal presentation for Gage and personal presentation to anyone who is interested in NMR. 20 minutes later, we will have spin operators for spin. And if you are doing NMR and Zeeman effect, you need connection between spin operators and observables from real life. And one of the observables is magnetization. If a material is magnetic, if you have some unpaired spins or nuclear spins, then how the magnetization of material relates to spin operators. So there is a proportionality coefficient between spin and magnetization vector, and it is code for magneton, which is like charge, time constant, and mass. So there is a direct proportionality between spin or angular momentum and magnetization. Bohr magnet. And if I would be able to show this slide by the end of the meeting, it will be a great success. So without details, the angular momentum can be characterized by a vector orthogonal to the plane of rotation. And the orientation of this vector would determine magnetic field, magnetization of an tube. But if you have who never heard the word gyroscope? Okay, who haven't? You all have, right? So it's just something spinning. Last year I was bringing bicycle wheel here. This year I'm lazy, but if you put bicycle wheel on the axis and then put a rope to this axle, it will not drop, right? But if you perform this, how you call them, when the axis rotates itself, like the wheel rotates around axis, and axis also performs rotation. Starts with letter P. Yes, perception. So, and if this wheel would be charged, the axle will be like orientation of magnetic field, and it will perform precession. So, same for this NMR spin. The magnetization vector has 3 components, which is not a wonder for 3-dimensional space. And if there is a external magnetic field, but there is an internal rotation, this magnetization vector, spin vector, will perform precession. With 3 components, x, y, and z, one can reproduce it as steady component in z direction and oscillating x and y components. If you were exposed to NMR, you probably saw this images or writings about it. Okay. And Alex will show this figure during his presentation. Right? It's not recall, it's how to say, expected result. So now you can fall asleep, relax. Yes, exactly. Camera was focused on the screen. I should put it on the class first. So while we are falling asleep, I will cover some boring math things which are needed for description of speed. So if you do have rotation, and you do have this definition of angular momentum is cross product of position of this rotating mass on a circle or orbit times momentum, right? And this vector is orthogonal to plane of rotation. How do we express it mathematically? So we need to, for each vector consists of 3 components. Okay? And we need mathematical operation that will develop resulting vector going out of plane. Like if you have vector R and vector P in one plane, we need vector L going outside of a plane.
Not a cross product?
Yes. You don't need, you're already educated. Right? Who never heard about cross product? Who can write down the equation for cross product? 1, 2, 3, 4. Okay, like majority. So if you have 3 projections for position, 3 projections for moment, we need to find 3 projections for angular momentum, right? And the cross product will be formulated as, since you already know it, it is just a little recall. It will be determinant of, so basis vectors, so those vector oriented in x, y, and z direction, then projections of position on x, y, and z, and projections of momentum of x, y, and z. So if one practices the rule to find determinant, it will be basis vector in x direction times determinant of this re. You already know how to find determinants. You presented them. So if you need stuff in front of I, you just remove this row and column, take this complement and find determinant of the complement. Right? And same for the rest of them. So this algebraic complements. Suppose we practiced enough and we did it. What are we going? What are we getting? So you all are physical chemists and quantum theorists. So sure, you're already successful researchers in this area, not just physical chemists. So what a physical chemist and quantum theorist thinks when he or she sees expression, like the word momentum expression P sub x? You expect it to think about quantum operator. So momentum is a gradient, derivative over position, right? With some constants like imaginary unit and Planck constant, right? Good. And in this, I'm going to flip back one slide. Here we do have momentum over y direction, over z direction, x direction, z direction. So when we are practicing this determinant, here it will be product y projection of position times momentum in z direction. Z of this is boring. Let's go to here. Why? Why I'm looking at the last one? Because it will correspond to our rigid rotor in xy plane, where the angular momentum will have z axis only. So projection of angular momentum in z direction will be projection of position in x times momentum in y minus projection of position in y times momentum in p. Make sense? And px will be derivative over x, py will be derivative over y. You see why I'm trying to exclude it from the main part of the course. It's a lot of writing and less thinking. So if we practice this thing, if we replace this px and py with derivatives, you will get this quantum operator for angular momentum. We already did it. We know that Lz will be just derivative over phi angle. Right? We already did it because we quickly jumped into spherical coordinates, and all educated people do so. But if you carefully progress through derivations, one needs to do through these things. So x derivative over y, derivative over x times y. So there is another property that I'm going to declare and not derive. Otherwise, we will die here. Or we will need another another semester. So again, since you were in the course for so long time, you also may have natural vision. If you see operator, you immediately want to apply it to a function, right? So all of these operators are designed to be applied to some wave functions, three-dimensional, because it is like three-dimensional rotation. So there is a property. If you will apply rotation in x and y by some angles to wave function, and if you apply the same rotations, operators of rotation in y and x in opposite direction, and subtract it, What are you going to get? Yeah, it can drive you crazy. It's a really edge of things that a human being can imagine via common sense, but it's already hard. So if one applies rotation in x and y on one hand, or in the opposite direction, y and x, this corresponds, like, if they would compensate each other, one should return to original angle, right? But no, instead, it will correspond to a small rotation along z. And this can be shown through algebra. Through rotations, and one should always assume that there is a wave function here and there, as we did for position and momentum. So if you would apply this x and y and x rotation to wave function that depends on three-dimensional, it will correspond to rotation along z. And if we would have a course for a year long, it will be a perfect homework. But we are lucky. You for not doing this homework, I'm not for grading it. So you do know that if one swaps the order of operators, it corresponds, how do you call it? Starts with C?
Commutation.
Yes. And if commutation is not equal to 0, then operators do not commute. Right? So x and y rotations do not commute, they give those in. And this is one of the points of connection between angular momentum and spin. Just make a little note in your brain or on your notes. So rotations in x and y do not commute, and they give rotation in z. And here is a little recall. Again, it is about a month or 2 months in the full-size course. If we formulate Hamiltonian of rotation, three-dimensional rigid rotor, which is x and y and z squared, then one can go into spherical coordinates, and then the solution will depend on two quantum numbers, orbital and magnetic, and can be variables can be separated for rotation in x, y plane, and depends only on phi, and another function depends only on theta. And we solved only for this phi capital, which is two-dimensional rotation. This one is ugly. And those of you who attended the class on the Wednesday before Thanksgiving have seen how they, well, some people, those who look on mathematical equations think they're ugly, those who look on visualization think they're pretty. They look like flowers. Okay, let's assume that we are done. Whew. Do you remember this figure from about 2 weeks ago? So it is energy associated with rigid rotor rotation and degeneracy. So for each value of energy, there are degeneracies. There are several quantum states matching the same energy, right? But in order to get this degeneracy, one needs to have true multidimensional rotation. If Michael and Gage are mimicking two-dimensional rotation with just a ring, this degeneracy will be not right. It is a good model, but not reproducing all things. It's like an approximation. But if you would have multidimensional rotation, you would have this degeneracy. And degeneracy for the lowest non-rotating s orbital is 1. For next one, analogous to p orbital, is 3, 5, 7. Agree. Now, if we try to be picky, rigorous, meticulous, and crazy simultaneously, one can ask a question like, why degeneracy jumps by steps of 2? Why do we have degeneracy 1 and 3, and we do not have degeneracy 2? Who forbids us to try degeneracy 2? Like, if angular momentum is 0, degeneracy is 1. If angular momentum quantum number is 1, degeneracy is 3. What should be the angular momentum to have degeneracy 2?
I?
Yes. So Alex made a discovery that if one plugs angular momentum on half, degeneracy will be 2. So you have introduced a spin for us. There is, you already tried, Gage and Michael tried fractional values of angular momentum, and they give something crazy, right? There is an analogy between angular momentum and spin. They have a lot of in common, but if you are speaking in public, I'm going to say something that please do not repeat. It's only for us just to get the main concept. So some people many years ago thought that spin is rotation of electron around itself, like a little sphere. When it rotates one direction, it is spin plus 1/2. When it rotates opposite direction, it is minus 1/2, given degeneracy 2. Why we shouldn't pronounce it in public? This is only to match our common sense vision. If one tries to pursue this model mathematically, it will give some crazy results, like no one saw the radius. No one can think of a spin of a hard sphere, of electron of a hard sphere. And if one would assume its rotation, then it should rotate much quicker than speed of light, which would be too many contradictions. So it is the existence of spin is just mathematical model. So if you find expectation values, observables based on spin, they will behave same way as observables for angular momentum. But angular momentum is easy to represent in the common sense imagination, and spin is not. So it is much more healthy for for just mental sanity. That it is just quantum number, plus 1/2 or minus 1/2. So there are two quantum states, up and down. Angular momentum, magnetic quantum number m plus 1/2, minus 1/2. Again, do not speak it in public. But what you can speak in public, that there are two spin states, up and down, plus 1/2, minus 1/2, or alpha and beta. Just by some reason, people like alpha and beta, probably because they are simplest Greek letters. So there many people. There are several ways to represent spin, and very often one represents it in Dirac notation. So ket vectors, alpha and beta, and expansion coefficients, c sub alpha, c sub beta. Great. Do you have time for anything else? Yes, we do. Generous 11 minutes. So I've told you all reasonable words to get common general understanding of what spin is. And now, if one wants to use it in practice, one needs to wrap up these ideas into mathematical representation. In some sense, this course, I don't know if you got this idea or not, but one of the goals of not exactly this course, but any physical chemistry theory is to learn how to become a translator. What we are doing in this course, we are translating concepts from human language to math language, and backwards, from math language to human language. Otherwise, those things are not possible. So it's time to translate these concepts onto math language. So if we represent quantum state as two basis states and two expansion coefficients, so it is vector in two-dimensional space with this expansion coefficient here, C alpha, C beta. We already know from our experience in quantum theory that expansion coefficients can be complex numbers, but there are just two of them. And the basis states, if you represent it in matrix notation, we can put it like this: C alpha and C beta can be C alpha times unit vector oriented in this direction and unit vector oriented in that direction, right? So alpha is same as two-dimensional space, where alpha means unit vector along x, and beta is unit vector along y. And spin state is something in this axis. Our second cornerstone for this piece of knowledge is ladder operator concepts for harmonic oscillator. Because through two operators, one can express any observable position, momentum, kinetic energy, potential energy, total energy, whatever one, well, everything that is needed for a system. The same situation is for spin. I'll tell you more. There is a substantial amount of physical chemistry and quantum theory courses that start studying from spin, like from lecture 1. Because mathematically it is the simplest one. So it is a little abstract, but mathematically it is really simple. So if you have lowest state and upper state, by the way, sometimes they are not split and the energies of alpha and beta spin are equal, but who knows? Generally, we can put them as lower and upper. And we can introduce ladder operators. S plus that promotes from lower to higher, and S minus that promotes from higher to lower. Right? So then this S plus acting on alpha will give you beta, S minus acting on beta will give you alpha. Right? So it is definition in Dirac notation. And if our alpha and beta are vectors in two-dimensional space, then these operators will be matrices in two-dimensional space, 2 by 2 matrices, right? How they would look like. So suppose that I have hidden this part. If this is our alpha state, we need to design such matrix that will generate from alpha will generate beta. So first element should be 0. So if we have here the row equals 0, row by column, we get 0. For the second one, row by column, we get 1. Right? Row by column results in 1. So these matrices are not Hermitian. If you do, no? Or they are? No? Are they Hermitian? But they're definitely non-diagonal. If one does conjugation and transpose, no, they are Hermitian. They're good. But typically, we deal with matrices that either have something on the diagonal or that are symmetric with respect to diagonal. Those are non-symmetric. So if we put this one opposite to a different corner, then it will act as S plus. So acting on the row by column on beta state, it will generate alpha state. Okay? So we do have raising and lowering operators in matrix form for spin 1/2. Same thing can be done in the Dirac notation, which is more appetizing. So if we formulate it as cat and bra, then it will be raising and lowering in Dirac notation. Here, if we apply the lowering operator to upper state, beta, we can repartition the set of cat, bra, cat as bra and cat here, that will give 1, and then remaining alpha will give you lowest state. Focus, focus. Right? Very convincing. And this operation is a little quicker than multiplication of matrices. And many problems in quantum recorders are typically formulated in this language. And an opposite experiment, if complementary experiment, if one would try to apply this annihilation operator to the lowest state, remember it was our main trick to find eigenstate of harmonic oscillator, right? Jumping lower than ground should give 0. So here, bra, repartition, looking on this part, beta times alpha, due to orthogonality, it will be 0. So if you just define the operator this way, it will give you 0. So, 3 minutes more. What is benefit? Does anyone in class benefit from this presentation and this lecture? Benefits for sure. If you want to update your report, look on the next 2 slides. I think a couple of people, maybe Alex. Well, so based on raising and lowering operators, one can express any other operators. There is no time for x, y, and z projection, but I will have time to show the energy operator in the case of this spin 1/2. So you'll see it in 2 slides. First, little mathematical experiment. What if you multiply this lowering and raising operators together? And remember, for harmonic oscillator, the product of raising and lowering were giving us Hamiltonian. Right? So multiplying these 2 matrices in this order, you give diagonal matrix with 1 at the top. Multiplying them in the opposite, you give diagonal matrix in the one in the lower order. If you add them together, it will be just unity matrix, identity operator. It's just math. It's boring and not useful. But now, what if we add these 2 things, these 2 components, not with unit components, but what if you put some other numbers? What if you put energy of state alpha and energy of state beta here up front of this operators?
Yeah, the energy of alpha in the top left corner, the energy of beta in the bottom right corner.
Yes. And this will be Hamiltonian, which is already diagonalized in diagonal form, right? Energy. So this is a little practical use of this tree. So this mathematical tool, this algebra of spin operators, is applicable to any 2-level system, not only to spin up-down. Anywhere where you can represent your system as 2 electronic states, 2 quantum states, one can use the same math. And then in the matrix notation, you already saw the Hamiltonian, and in the Dirac notation, so E alpha, alpha alpha, E beta, beta beta. So it's a standard form to express the Hamiltonian. Let me see what else I have. We kind of got this table, right? If you summarize what we did. And if, okay, no time. If we would cast the Heisenberg equation of motion for these operators and add together plus and minus operators, then one would get projections and harmonic rotation of the magnetization in x and y direction. Enough. Let me know if you want to hear more about that, but our time is over. Stop by if you want to chat about anything. And last formal lecture on Wednesday will be on Frank quantum factor for UV structures. Thank you.